So let's take a look at this test 3. Um, so let's take a look at this. First problem is fairly simple. Um, I did forget to put a horizontal line across here, but let me. So what I'm going to do, try to save this. I'll just save it. I'm sorry for taking this extra few minutes. I'm going to try to. Well, that is not where I wanted to bring it up in. Alright, here's why I wanted to bring it up in here. Okay, I can write on it. So in this one, okay, this part right here can't move to the right or cannot move up. It is fixed, tied to the ground. Point C here can move this way or it can move that way, but it cannot move up or down. So this means there is no reaction force like this at point C. There is a reaction force up. There is a reaction force up here, and there's a reaction force to the right here. With all that, you have to choose which way you want to solve this. You can choose method of sections, and you could just section things off like that, or you could go node at a time. The coordinates are given. They're not that great. To get to D, you move over 6, 5, and 6. That'd be 12 or 17 in the X direction, and 5 and 2 or 7 in the Y direction. Likewise, 6 and 5 gives you 11, and that's at a Y of 0. B sits up here at 6 over and 5 up, and of course A sits at the origin. So all the coordinates are determinable. Let's go ahead and look at the next problem here. This one is kind of unique. Instead of putting the dimensions all over it, I decided to list a little matrix of the coordinates. So for example, A is at the origin, B is 3 over but 6 up, C is 5 over but not moving nowhere up in the it's y coordinate 0. Same thing with E sitting here. D on the other hand is 6 up, just like B at the same height. D is moved to the right 10. F is in a strange location 17 and 4, and G is at 23 and 7. These coordinates were done to scale. This paper is engineering paper, so the lines are not there because of the scan the way I did it, but they are there. The only load on this structure happens to be a 5,000 pound load put perpendicular to member F and G. If you notice, I did not ask for the loads in F and G. F and G is a kind of unique load, and that F and G is a unique member, in that, unlike, everything, let me first state, everything is a pin. All of these are pins. Let me also state this one can only move to the right or to the left. So it has a reaction load up, but no left and right reaction loads. So essentially what you get for the reaction is this, some load here, some load there, and that's pretty much it. What are those? I don't know. That's what you're supposed to determine. But the key is, if we take a look at F to G for a moment, if we just look at it, there's something unique about it. If you look at it, the wall can push back this way against point G. So you could almost put a load right here on point G. I've stated that whatever the length of this thing is, and you'll have to figure out the length of this thing, you can figure it out from Pythagorean theorem or whatever. And halfway in between is where this load is placed. Now, if you go over here to, like, say, let's go over here and look at a beam. I'm not saying that it's exactly the dimensions, but let's just say you had a situation just like that, where there is no vertical load here. That doesn't exist. This point of the beam can move up or down freely. The 5,000 pound actually does something quite interesting. It wedges this beam down, so as this kind of moves down, this force pushes against the whole structure. So this 5,000 pound pushes this down on this FG, and it actually is a beam. Here's what I mean. Here's the difference between a beam and a bar. You have two nodes, pins here. If you have tonally axial loads like a tension load or a compressive load, then that's a bar. If in fact though you do something like this to it, then you have to have a reactionary load back here. Now, as it turns out, in the structure we have exactly this. So if we find a common place to sum the moments about, if I pick this point, it's an arbitrary created point, say P, and I sum the moments about P, what I'll determine is this force produces no moment about P. Neither does this force. So those two forces don't create a moment about P. So this means that this force has to go right through P as well. Again, the geometry can figure out this. You can figure out the geometry from everything. Then what you do, believe it or not, right, move this over to the side. You can pull this point away from the structure and take this exact load right here and put equal and opposite on there. So this is equal, opposite. This is the load put on the truss. This is the load from the beam. So that's kind of the secret to doing this one. You'll have to go in. You will have to figure out the load here. You'll have to figure out the load here. You'll have to figure out the load here. From the wall load pushing here, you're going to have an equivalent load that comes through here. So then you just figure out whether it's in tension or compression, each of these members. Same thing back here. Is it in tension or compression? And that's pretty much it.